Look at the volume of data pulsing across these global fiber optic networks. Right now, millions of encrypted transactions, private messages, and secure bank transfers are traveling between continents in fractions of a second. But the network carrying this information was never designed for this level of sensitivity. In 1989, the World Wide Web was built as a platform for scientists to share academic documents across an open network. Tim Berners-Lee created the communication rules that made this global web of information possible. A network designed for the open exchange of research papers is now the base layer for global finance. Bridging this gap requires two specific protocols. HTTP defines the rules for moving data, and HTTPS provides the cryptographic layer that shields it. For a blockchain developer, these protocols determine how web-based interfaces and wallets interact with decentralized networks. At its most basic level, HTTP is a client-server communication model. A client sends a request, and the server returns a response. In this model, your web browser acts as the active client, initiating the exchange by pinging the server. HTTP is a stateless protocol. Every request is an independent event. Once the server sends its response, it does not retain any memory of the interaction, treating the next request from that same browser as a brand new encounter. The client identifies the resource it needs using a Uniform Resource Locator, or URL. Every URL follows a standardized syntax that contains several distinct pieces of information. The first half establishes the connection. The protocol tells the browser which set of rules to use, while the domain name identifies the specific server to contact. The second half handles navigation. The path directs the server to a specific folder, and the resource specifies the exact file to retrieve. To tell the server what to do with that resource, the client uses specific HTTP methods. A GET request retrieves data, such as loading a web page. A POST request submits new data to the server, like sending a login form. PUT is used to update existing data on the server, while delete removes a resource entirely. The server communicates the result of these actions using numerical status codes. A 200-level code indicates a successful operation. This is contrasted with failure codes. 400-level codes signal a client error, like a broken URL, and 500-level codes indicate a failure on the server's end. This standardized syntax allows the web to scale across millions of servers, but the protocol itself does not include any built-in security features. Standard HTTP communicates in plain text. Every byte of data, including POST requests containing passwords, travels across the network as unencrypted, readable data. This is a vulnerability because of how the internet is built. Data does not travel directly from your computer to the server. It hops through multiple intermediate routers and infrastructure points. At any of these points, a malicious actor can perform a man-in-the-middle attack. They intercept the data as it passes through and read the plain text without the client or server ever knowing the connection was compromised. In the early era of the web, this was an acceptable risk because most traffic consisted of public academic documents. Today, we use this same network to log into bank accounts and submit private cryptographic keys. Exposing financial or Web3 transactions to intermediate monitors is catastrophic. To handle sensitive data, the internet required a cryptographic solution. HTTPS provides that solution by wrapping standard HTTP in a secondary security layer called Transport Layer Security, or TLS. Before any data is exchanged, the client and server execute a TLS handshake to establish a secure connection. The process begins when the browser connects to the server and shares the encryption algorithms it supports. The server responds by selecting an encryption method and sending its digital certificate to prove its identity. Through an asymmetric key exchange, both parties create an identical shared session key. This key is created locally on both sides without ever being sent across the network. All subsequent HTTP communication is encrypted with this session key. The plain text data is now sealed inside an unreadable ciphertext shell before it leaves the client. This entire negotiation completes in under 100 milliseconds, often requiring multiple round trips across the globe. Underneath this layer, the HTTP structure remains the same. TLS simply provides a secure transport tunnel for the requests and responses. Encryption alone does not ensure security. You could negotiate a perfect TLS handshake with a fraudulent server that is simply pretending to be your bank. This is why we use certificate authorities. These are trusted organizations that verify the identity of a website owner and issue a mathematically signed certificate to legitimate servers. When your browser receives a certificate during the handshake, it checks the digital signature against a pre-installed list of trusted authorities to verify the server's identity. A successful match triggers the padlock icon in your address bar, signaling that the connection is both encrypted and verified. Subsequent iterations of the protocol have focused on speed. HTTPS 2 introduced multiplexing to handle multiple requests at once, and HTTPS 3 uses a protocol called QUIC to establish these secure links faster. This combination of encryption and verified identity is the base layer of trust for digital commerce. There is a common misconception that blockchain systems bypass these web protocols by operating on purely proprietary peer-to-peer networks. While backend nodes communicate peer-to-peer, the user applications you touch, like MetaMask, rely on HTTPS. When checking a balance or submitting a transaction, your browser sends an HTTPS request to an API endpoint, protected by the exact same TLS encryption used in standard banking. The asymmetric cryptography used for a TLS session key relies on the same public and private key principles that secure your blockchain assets. Web protocols are the foundation that allow user-facing blockchain applications to function securely. This entire system relies on knowing the exact IP address of the server you need. In the next video, we will look at the system that translates human-readable text into the numerical addresses computers use, the domain name system.